Hi everyone, thanks for tuning into my Stacks presentation. So this is Nick Banks talking to you about Etale cohomology groups and the Weil conjectures today. So here's the outline of topics. First we'll discuss the motivation for the Etale cohomology groups and what the intention was for defining them and how you actually define them. We'll compute an example, talk about some properties. We'll talk about a variant on the Etale cohomology called the l-adic cohomology. And then we'll talk about how they were used to prove the Weil conjectures in the 60s and 70s. So, why Etale cohomology? They were introduced by Grothendieck in order to prove the Weil conjectures. The Weil conjectures were extremely influential set of 4 conjectures put forth by André Weil. It's not much of a stretch to say that those conjectures really are the reason for a lot of what we study in algebraic geometry, modern algebraic geometry. So if you know about the Riemann hypothesis, these were sort of analogs of those for schemes or projective varieties over finite fields. Weil suggested, shortly after he posed the conjectures, that they could be proved if we had something called the Weil cohomology theory. Weil didn't call it that, but it came to be called that, which is a cohomology theory that has a set of really nice properties. It turns out the l-adic cohomology was an example. It's one of the first examples that was specifically set forth to be a Weil cohomology theory. And he was right. It turned out that that was central in proving his conjectures. So the reason that they needed a new cohomology theory is that the traditional cohomology at the time was the singular or simplicial cohomology of things like, in algebraic topology, of things like complex topological spaces and things like that, which, but if you look at the properties for a Weil cohomology theory, they couldn't have coefficients in Q, which is normally where they would be for those cohomology theories that existed. So we needed a new theory which played nicely with finite fields, in particular with the prime characteristic. Okay, how do we define it? Well, anytime you have a cohomology theory, it comes about because you have a left exact functor that's not always right exact. So in this case, we're going to let X be a scheme. We're going to consider the small Etale site of X. So remember, those objects in that site are Etale maps from some scheme Y to X. And the objects are commutative triangles of 2 things like that, which I'm sure you remember. And you can define a covering in a pretty simple way for this site. So if F is a sheaf of abelian groups on X, then we use this sort of notation for the global sections. So if I want to specify the site that we're working with, I'll put an ET down there, but usually I just put gamma of X and F, which is just another way of saying we apply the sheaf of abelian groups to the whole set X, the whole space X. So we can ask whether this gives a functor. I gave it a name down here, gamma of X and star is a functor. You give it a sheaf on X on the Etale site, and you get an abelian group, so it's a functor. You can ask whether it's exact, which means I have a short exact sequence of sheaves here on the Etale site. I can apply global sections at each step. And so where do these induced maps come from? Well, the data of a morphism of sheaves includes a map between global sections, so we're just taking that specific piece of the data to get this induced sequence. It turns out that this part is exact, so we preserve injectivity at this map between F and G. We preserve exactness here, but that map between G and H is in the first sequence is surjective, but on global sections it may not be surjective. So basically, when we take global sections, we might get too many, depending on the sheaf that we're using. Okay, well, since it preserves exactness everywhere except on the right, we say that it's a left exact functor, this gamma X and star functor. There's multiple ways to prove that. One of them is just unraveling definitions, doing a kind of diagram chase. Maybe a slick way to see it is that this is the right adjoint of a functor, this constant sheaf functor, which you might have seen before. So it's the right adjoint, and it's kind of clear that this constant sheaf functor is right exact. It's easier to see than with the global sections. And the right adjoint of a right exact functor is always left exact. Okay, but why does it fail to be right exact? Oh, I should mention that you can make this definition for any site. I just am specializing to the small Etale site, but for example, you could do the small Zariski site or the FPPF, or any of the ones we looked at in class, basically, if you have a sheaf on that site. In particular, the Etale site is sort of contains the Zariski site, so the Zariski site is more coarse, so we can kind of apply the same idea directly to the Zariski topology. So that's what this example will be, just because it's the simplest one I could find. Uses the Zariski site. So let X be the projective line over C. O, or O of 0, will its structure sheaf. And CP, so P is any point in the complexes, and CP is the skyscraper sheaf. So it's either the trivial group or the complex numbers, depending on if P is in the open set that you consider. So hopefully it's clear. We have a surjection from the structure sheaf to the skyscraper sheaf, and the kernel is this twisting sheaf O minus 1. So we can twist by O minus 1. It just means tensor with that at every stage here. So when we tensor O minus 1 with itself, we get O minus 2. With O, we get O minus 1. And when you twist CP, it stays the same. So that's where this short exact sequence comes from. Okay, so let's take global sections and see whether we get surjectivity. We know that this is exact, but the question is, does it stay exact on the right? Is this map surjective? It turns out it's not, because, well, you've probably seen before that there are no global sections of this O minus 1 sheaf, no non-trivial global sections, so it's 0. And it's pretty clear to see that the sections of this skyscraper sheaf are all of the complex plane. So, it's a sequence that goes from 0 to the complexes. Clearly that's not surjective. And maybe a highfalutin way of saying the same thing is that the first cohomology of this variety P1 in this case with the sheaf O minus 2, you can show that that's equal to C, and this thing up here would be exact precisely when this cohomology group is 0, so that's a measure of how it fails to be exact. So we get too many sections of the skyscraper sheaf and not enough of O minus 1. And this is a pretty simple example. Like I said, it's the Zariski site, it's not even the Etale site, so we're not using the full power of the theory, and already it fails in this simple example. So no doubt it will fail in more complicated cases as well. So the category theory says that we can fix this. So the category of sheaves of abelian groups on X is this technical condition, which satisfies this technical condition of having enough injectives. That means we can always find a monomorphism from such a sheaf to a particularly nice sheaf called an injective object. And if that's the case, then the category theory says we can always take what's called the right-derived functors of that global sections functor. That means, okay, what comes next after this part up here that we know to be exact? Well, that's a right-derived functor, and we just call it the first cohomology group of X with coefficients in F, and I specify that it's with the Etale site of X, although you can see it's pretty standard to not write that if you know what the site is. So yeah, the right-derived functors are just what comes after this exact row up here to make the rest of the sequence exact, and generally it won't be short exact, and in particular the size of that first one sort of measures how much it fails to be exact. And these group homomorphisms like delta 0, delta 1, etc. The category theory again tells us those exist, and so everything is nice and dandy. Just the unify notation is common to denote the gamma of x and f, the global sections, by h0. So h0 is sort of defined to be the global sections. So hi of x and f, I already used this terminology, but just to make it official, it's called the ith Etale cohomology group of x with coefficients in f. So this use of the word coefficients is kind of just an artifact of the history of the theory. It's not actually like an algebraic coefficient, so don't take it too seriously. But it is what people say. Okay. So, summary, the Etale cohomology groups make the global sections of sheaves of the Etale site exact. The catch is that it's not always short, not usually a short exact sequence. So let's look at an example. The example is going to be these multiplicative sheaves, namely let x be a smooth projective curve. Actually, I think what I write here works for a higher dimensional variety, but we do want it to be over an algebraically closed field K. So we're going to consider the sheaf, which is variously called GM or just OX star, so it's the sheaf of units. So that's a multiplicative abelian group, sheaf of multiplicative abelian groups on X. And by basic geometry, you might remember the sections of that sheaf is just non-zero constant, so K star in this case. What about H1? Well, it turns out that there's a natural isomorphism between the first cohomology with coefficients there in GM with the Picard group of X. So for purposes of this slide, you can think of the Picard group as being isomorphism classes of invertible sheaves of X on X. Now, how do we prove that? So there's going to be, even in these simple examples, it's going to be some hand-waving, some shoving stuff under the rug. The first thing we would need to do, if I wanted to give a full proof, is to show that there is a natural bijection between H1 of X and F. Actually, for any site, I believe it works in any sheaf of abelian groups. It's naturally in bijection with the set of the set of isomorphism classes. Okay, it looks like the O doesn't want to stay. Isomorphism classes of F torsors. Why do the O's keep disappearing? That's weird. Okay, anyway, so this is the first thing we might want to prove. This is a connection between torsors and the first cohomology group of a sheaf of X with respect to a sheaf. Now, this isn't actually too hard to prove. You just kind of unravel definitions and you can construct explicitly this bijection. So that means in order to prove this isomorphism that we're talking about, we would just show that invertible sheaves, not isomorphism classes, but just invertible sheaves themselves, are I was trying to erase, and that's messy. Okay, anyway, hopefully it's not too distracting. We would show that the not isomorphism classes, just invertible sheaves on X, which is like the bigger version of the Picard group, is equivalent to the category of GM torsors on the Etale site, and that would descend to a equivalence on isomorphism classes, and that would give us what we want. Okay, so how do we do that? So take L, an invertible sheaf on X, and F from Y to X in Etale map. We define this this GM torsor L star of Y is the isomorphisms from the structure sheaf on Y to the pullback of L by F by this Etale map. And so the proof that this is actually a GM torsor follows from the properties of Etale maps that we've seen throughout the class. So I guess I'll say something about the other direction. So this is one direction of the equivalence. To get from a torsor to an invertible sheaf on X, you would need to you would argue that you can take a finite Etale cover of the space X such that the torsor that you're considering, the GM torsor, is always trivial when you restrict to that cover, to the open sets, to the sets in that cover. And so again, that's it takes us too far afield, so I won't show it, but that's the idea. And so then this equivalence descends to 1 on isomorphism classes, and this gives us that H1 of X in GM is the same as the Picard group. You can also show, but again, this is even more involved and takes us too far afield, but you can show that the higher cohomology of X with coefficients in GM vanishes. So it's only the 0th and the first ones that are interesting. Okay. So by the way, even in that simple example, it's pretty involved, as you can see. But now let's talk about some sort of characterizing properties of Etale cohomology. So the first one is called the proper base change theorem. So basically we start with this Cartesian diagram here. Put the little, I don't know how to do this in LaTeX, but this is like a right angle that we use for a Cartesian diagram. So we got schemes X, S, and T. The map from X to S is a proper map. The map F here is just any map of schemes. And X prime is the pullback of this diagram. So that's the setup. And the theorem is that if we have F, any sheaf of torsion groups, so that's sheaves of abelian groups where they're all torsion groups. And in such a case, we have a canonical isomorphism between these two things. So this R pi star functor, I believe it's called I always get them mixed up. Actually, no, the whole thing together is called something like the derived push-pull or the pull-push. I can't remember which order we say it in. But this one is the derived push-pull, I want to say, and this one's the derived pull-push functor. Anyway, these are just special functors. They're defined in terms of limits of cohomology groups where the schemes you're taking them over are the preimages under pi, under this proper map. So suffice to say, this theorem says that the cohomology, the Etale cohomology, plays nicely with limits and pulling back and pushing forward. That's all you need to know about it, really. So we got something called the comparison theorem. Well, X be a variety over C, and X to the A and its analytification. So I don't know if you've seen that term before. It basically just means, consider X as a topological space, some kind of topological subspace of the complexes. It's a more technical definition you can make if you want. But the comparison theorem says for all I, there's a natural isomorphism between the Etale cohomology of X and what's sometimes called the ordinary cohomology. It's basically, you could think of the singular cohomology or maybe the simplicial cohomology, the ones you learn in algebraic topology. So those are naturally isomorphic. The catch is that you need to take the coefficients to be in some finite abelian group A. Well, technically some constant sheaf with values in a finite abelian group. So you can't take the coefficients from anywhere, but if you take them to be well chosen, then these are always the same, which is maybe surprising. Okay, another important theorem, so the last one we'll look at for now, is called the Lefschetz fixed point formula. So if X is a complete smooth variety over algebraically closed field K, we have some self-map phi, which is also regular on X. Then we have this formula. So the left-hand side, gamma phi is the graph of phi, and delta X is the diagonal on X. So this product on the left is basically counting the number of fixed points of the map phi, so the points in X that are not moved. And in this case that I mentioned up here, the assumptions on X, it turns out is finite. And you can compute them in terms of the cohomology groups of X with well-chosen coefficients. Specifically, you take the map phi and it descends to a map on what ends up being a vector space here. They take the coefficients in the proper place. So you take the trace of that map, and you can view it as a matrix if you want, because these are all finite dimensional vector spaces. And so you compute the trace and take this alternating sum, and that gives you exactly the number of fixed points of the map phi. So the name Lefschetz is attached to, he proved an earlier version of this for a different cohomology theory, I think probably for singular cohomology, but it just has his name because of the similarities. Right, so these, like I said, these properties more or less characterize the Etale cohomology, along with some other technical ones that I didn't want to get into, and they were all important for proving the Weil conjectures. So speaking of the Weil conjectures, let's talk about the l-adic cohomology groups. These are sort of a variant on the Etale cohomology that were really the central ones in proving the conjectures. So for this cohomology, we're going to be working over a finite field fq. So q is the number of elements, so some power of a prime p. So p is the characteristic. And if we take another prime L, which is not equal to P, so it's kind of an amusing story. People say that Grothendieck was the one that proved you can use L to stand for a prime, because that's what he did when he introduced l-adic cohomology. This definition is kind of an abusive, well, it is an abusive notation, so bear with me. But for this prime L, what we can do is we can take, on the right-hand side here, the Etale cohomology of the ith Etale cohomology, fixed I, of x with coefficients in, well, technically in the constant sheaf with values in this finite abelian group. So mod some power of that prime L that we picked. And this gives you an inverse system of groups, and you can take the inverse limit. It's category theoretical construction, and you get, we define that to be denoted by hi of x comma zl. So zl is usually used to stand for the l-adic integers, which is like, you can think of formal power series with powers in L. Now, just a word of caution, okay? Hi, if I had written hi of x and zl before, that's a notation that would have made sense before. We would have thought, oh, it's the ith Etale cohomology with of x with coefficients in the constant sheaf zl, the l-adic integers. It's a perfectly reasonable thing to think, but it's not the same as this. This is not equal to what I just explained in words is not equal to this co-limit, this inverse limit. So it's a common misconception. Yeah, it's an unfortunate notation, but it is what it is. So sometimes it's nice to have a vector space over a field. So the second definition, again, abusive terminology, or abusive notation rather. QL is the l-adic numbers, the field of fractions of ZL. That's just the tensor of that group up above with QL, and that makes it into a vector space over QL. So sometimes it's nice to have that. Okay, so what are some new properties of the l-adic cohomology? So X is an n-dimensional smooth projective variety over a field K. No longer needs to be algebraically closed, I think. P is the characteristic, so typically we're interested in when that's a prime. So something new here is that we have this F, this field F, which is called the field of coefficients. It's a field of characteristic 0, and we pick some prime L. Again, that's not P. So this co-limit of this inverse limit that we defined earlier of Etale cohomology groups, the l-adic cohomology of X, is a finite dimensional graded F algebra for all indices I, so that's sort of the least we could expect, and that's the first place where this F comes up. Just the field where these things are algebras over. Typically some number field, I think. Okay, so this is for all integers, even negative ones, but it turns out all the negative ones are 0. So the 0th one is the first one that comes up. and the highest one is twice the dimension of x of the variety. And speaking of that highest indexed group, it turns out to be isomorphic to the field of coefficients. That's again another place where that field comes up. Here are some important properties. So these are sort of more basic properties, but more involved things I'll talk about here. So the first one is called Poincare duality. Again, the name is kind of carried over from a theorem that Poincare proved for sort of ordinary cohomology, but it persists. So it says that there's a perfect pairing between these two cohomology groups where the sort of reflect around the top non-zero cohomology group, the 2nth one, which we know is isomorphic to F. And so a perfect pairing essentially means that that this is an isomorphism. So that's a good calculational tool. We also have something called the Kuhneth formula. So it relates the l-adic cohomology of a product with the individual ones, and in particular it's isomorphic to the tensor of the two individual groups. Okay, so yeah, like I said, these properties were more or less all used to prove the Weil conjectures. So let's look at the Weil conjectures and how they followed. So I mentioned at the very beginning, the Weil conjectures are sort of looking at sort of analogies of the Riemann zeta function and the Riemann hypothesis for varieties over finite fields. So let's remind ourselves what those things are. So the Riemann zeta function, naively you define it for complex numbers S with a real part bigger than 1. You define it as this infinite sum of the reciprocals of powers. But it turns out part of the work that Riemann did with this is that you can analytically continue this to a function which is holomorphic everywhere on C except at 1, which is a pole that we can't remove. And it turns out, so this looks like maybe sort of some kind of analytic object, but it turns out this has a deep connection with the distribution of primes. So this is called the Euler product. The Euler product form of the zeta function, proved by Euler, more or less. So it's zeta s is equal to the product over all primes in z of this rational function of primes. And what's interesting is that the way you prove it is more or less shows that it's equivalent to unique factorization of integers into primes. So we'll look at this. Will help us define it for an arbitrary variety. The second one is that we have this functional equation. This new program I'm using for writing is not the best. Functional equation. So, functional equation basically relates zeta of s to zeta of 1 minus s. It's like a reflection formula. Don't worry about this junk out the middle. Although of note is that there's a sign. It's multiplied by sine of some argument. In particular, if s is negative an even integer, so minus 2n for some integer n, then this is trivially 0. So those are called the trivial zeros of the zeta function. Otherwise, it's been conjectured that all the zeros of the zeta function, besides those trivial ones, have real part equal to a half, so this is called the Riemann hypothesis. So I put it in properties, but it's actually not been proved. Probably one of the most famous unsolved problems in math at the moment. So what we're going to do is use some of these properties to define an analogous zeta function for a variety over a finite field, and then look at some properties that remind us of these. So zeta function of a variety. Let X be some n-dimensional smooth projective variety over a finite field with Q elements, characteristic P, so Q is some power of P. But working over a finite field, something we can define is the number of points when we extend from FQ to some power of M, so a degree M extension of FQ. So we can extend and we can count the number of points since it's still a finite field, and that number is called n sub m. So we can define the zeta function of x evaluated at s, where s is a complex number with real part s bigger than 1, like in that naive definition of the Riemann function. So the first way we define it is analogous to the Euler product. I think some people still call it an Euler product, even though Euler wouldn't have proved this part. So hopefully it reminds you of property 1 here. Instead of primes, we now take the product over all points of x. And this p that appears in this rational expression in the product is now the norm of the point x. So what's that? That is basically the size of the residue field of x. So when it's a prime in the integers, the size of the residue field and the number itself are the same, but in general we have to take this extra step. Okay. So you play around with this formula, and you take in particular, you take the natural log of it, and you end up being able to relate the norm here to the number of points in some extension. It's not a hard proof, but again, too far afield. So you take the log of that, and you get this, and you use the power series of log basically, and you get what's in brackets here. So that means another way to define the zeta function is as the exponential of this sum. It looks almost like a generating function of the number of points with the variable equal to q to the minus s. So an analogy with the Riemann zeta function, which is sort of a generating function for the primes in z. Okay, so that's the zeta function of a variety. So here are the conjectures, which they're still called conjectures usually, but they've been proved. So there's the rationality conjecture, which says that the zeta function of such a variety is a ratio of polynomials, each of these polynomials being having integer coefficients. So the second conjecture is called the functional equation conjecture, which says that if chi is the Euler characteristic of the variety x, then we get this reflection formula. So remember, in the zeta for the Riemann function, it was zeta of 1 minus s. Well, now it's zeta of n minus s being related to just zeta of s, multiplying by this junk out here. It's not really too important what this stuff is, although of interest is that you might have heard of the Euler characteristic defined for like a simplicial surface, or like a polyhedral surface or something. It's so part of the challenge of the conjectures is defining the Euler characteristic in a way, in a consistent way for arbitrary varieties over finite fields, for example. And we were able to do that. It was a homological notion, it turns out. That's the functional equation. Then there's the analog of the Riemann hypothesis, which says that the zeros of those rational, of these polynomials up here, all have, the zeros of each part lie on a so-called critical line, a vertical line in the complex plane. They all have the same real part. And hopefully you see an analogy with that and the Riemann hypothesis for the Riemann function. So if you know the zeros of those polynomials, then of course you know all the zeros of zeta itself. And the final conjecture is the Betti numbers conjecture. So if x comes from some analytic variety, basically, then we can relate the degrees of those polynomials to the Betti numbers of y considered as a complex space. So in more detail, suppose that y is a smooth projective variety defined over some number field that's a finite extension of the rationals, so you can in particular embed it into the complexes. if X is a good reduction, mod P of that variety over that you can embed into C, into projector space over C. So good reduction I'm not going to get into, but most primes are good reductions. So if that's the case, if X comes from Y in this manner, then the zeta function of Y, the integral polynomials that express the zeta function of X are equal to the ith Betti numbers of the variety Y considered as a complex space. So this is maybe the most surprising conjecture to me, I think, because it relates this sort of discrete information. The zeta function of X is very much a discrete object. It's counting number of points of something, whereas the Betti numbers are a topological notion, so it's sort of in the continuous world, so it's a surprise that they're related. Oh, sorry, I know I'm a little bit over time. Hopefully your attention is still with me. So I'll just say a couple words about how these were proved. So all of the conjectures except for the Riemann hypothesis one were they're credited to Grothendieck. Hopefully I spelled his name right. Grothendieck, someone named Dwork, someone named Verdier, so some of Grothendieck's collaborators, and also Michael Artin. They proved the first three of the conjectures, not including the Riemann hypothesis one, using the theory of l-adic cohomology. So I'll just say a little bit about how they did that. So for the rationality one, they applied the Lefschetz formula that we looked at up here to the Frobenius automorphism, or the Frobenius map, which is a map. It's a p-th power map if p is the characteristic of the field. So it's sort of an ingenious idea, and they were able to apply that, take the trace of it on the cohomology, and get the number of fixed points, and this gave them a rational expression for the zeta function of X. For the functional equation, I think they used Poincare duality mainly to prove that, so that's this perfect pairing between l-adic cohomology. And the Betti numbers followed from the comparison theorem, which says that in certain assumptions, the Etale cohomology is equal to the analytic cohomology, or the singular cohomology of the analytification. And Deligne was the one who proved this. So I think the other proofs were done in like the early 60s, mid-60s. It won't let me write, but okay. Pierre Deligne was the one who proved the Riemann hypothesis conjecture in the 70s, 1974 or so, and he used something called the Leray spectral sequence, which is, if you know about Hodge theory, it's sort of something like that, analogies of that for the l-adic and Etale cohomologies. Okay, so that's all I had to say. I hope you learned something. Here's the references I used if you're interested. And like I said, I'm happy to answer questions by email or Teams or wherever you want to reach me. Okay, thanks.